Hello everybody. Today we're going to talk about something that's sort of supplemental. It is a completely pre-calculus topic. This is not anything to do with calculus, but I did want to go over it just in case our pre-calculus skills were kind of shaky. I did see some need for review on these topics, so I thought it would be good to create a video for you guys. So, we're going to go over some trig concepts, and our objectives for this video are to remember how to construct a unit circle. And really, my goal here is just to remind you guys of where all of the values on the unit circle come from and how they're useful in remembering key components of trigonometric graphs, of things like sine, cosine, tangent, and so on. I'd also want to define period of a trigonometric function and why it is derived the way that it is. And then lastly, I would like to develop properties of the 6 inverse trigonometric functions, and this is that objective, if you remember from the last video, that we saved for today. Alright, so first things first, we're going to construct a unit circle. I've already drawn my circle because I wanted to make it look a little bit nicer. And I'd like to start off with just adding in the information that's really easy to add to this thing. Remember that a unit circle is defined as having a radius of 1. So when we throw it on the coordinate plane and we center it at 0, 0, we know that this point, if we just use our basic knowledge of a coordinate plane, has to be 1, 0. This point has to be 0, 1. Over here we must have negative 1, 0, and lastly we must have 0, negative 1. Nothing new there. That's just the basics of a coordinate plane. Next, what we can add in pretty easily are some radian values. We know that for every 180 degrees, right, for every half of a circle, we have 1 pi. And I'm also going to write the degree value there as well, 180 degrees. We know that for every 90, if we go around this circle, right here we would have 90 degrees. We would have halfway between here and here, halfway between pi, so we would have pi over 2. And if we go around the circle again, we have another pi, or we have 2 pi. And then if we went halfway, if we went 1.5, we would get 1.5 pi, or 3 pi over 2. And if we remember every 90 degrees, this is 270 degrees. And lastly, if we come full circle, we get 360 degrees. Okay, not so bad. Now, let's start breaking this up into useful pieces. And the values we're going to break it up into are going to lead into us reviewing special right triangles. And so the degree values we're going to use in every little quadrant here are going to be every 30, every 45, and every 60 degrees. So if we made a point right here at about 30 degrees, again, about 30 degrees up right here, can label it 30 degrees. And then if we think about it, if we keep going by 30 degrees, that's how we would get our 60 degrees. And if we kept doing this, you guys, we would split this top half into 1, 2, 3, 4, 5, 6 pieces. So in radians, we'd split this 1 pi into 6 pieces. Every 30 degrees is a pi over 6. And for 60 degrees, we'd have 2 pi over 6, so we know 2 over 6 to just be 1/3, or pi over 3. Here we'd have 4 over 6. Oh, pardon me, we'd have 3 over 6 here. 3 over 6, and then with our next 30 degrees, we'd have 4 over 6, but again, we know how to reduce fractions, so we know that that would be 2/3 pi. And that would be at 120 degrees. If we made another 30-degree point, that would be 150 degrees. And if we kept going by those sixes, we'd have 1, 2, 3, 4, 5 sixths pi. Awesome. And let's just keep filling in our every 30 degrees and every sixths. It's always fun to say sixths. All right, so this 30 degrees, if we added 30 to 80, we would get 210 degrees. And then in radians, that would be one more sixth. We'd have 7 over 6 pi. And if we add another 30 degrees, we would have 240. And then that would be 8 over 6, but we remember how to reduce, so that would be 4/3 pi. If we add another 30 degrees here, we would be at 300 degrees. And if we counted our sixth, that would be 10 over 6 or 5 over 3 pi. And if we kept going, this would be 330 degrees. And then if we added our sixths again, that's always so fun to do. All right, we would have 11 over 6 pi. Let me double check to make sure I am correct in that. I'm fairly certain I am. All right, I am. 11 over 6 pi. Great, that takes care of all of our 30 degrees, but then we also have one right in the middle of all of these at every 45 degrees. So we're going to fill those in last, right in between. Every 45, we can see that we're also splitting those up into fourths now. If we split up this whole thing, every 45 would happen every 1, 2, 3, 4. So we can make that pi over 4 radians. And over here we would have 3/4 radians. And in degrees, every 45, that would be 135 degrees. And down here, another 45 degrees would give us 5 over 4 pi radians. And we would be at 225 degrees. And again, I'm getting this just by adding 45 degrees every time and counting by fourths. So here I would have 6 over 4, which we know would be 3 over 2. If I add another one, I would have 7 over 4 pi. And if I added my 45 degrees between here and here, I would get 315 degrees. All right. So that is where all of the degree values are derived from, and these 4 coordinates are derived from, and that's also where all of our radian values come from. There's nothing really special about them, it's just how we break up the unit circle. What I have to show you next is rather interesting, and it isn't as obvious. We fill in, you guys know that there are coordinate values for every one of these points, and we fill those in using our knowledge of cosine and sine. What do we call those? Trigonometric ratios, the trigonometric ratios of sine and cosine. So right up here, let's write a little reminder for ourselves about what those mean. Cosine, we remember, is the adjacent side over the hypotenuse. And sine, we remember, is the opposite side over the hypotenuse. And for the sake of the unit circle, remember that your sine values are your y's for every coordinate, and your cosine values are your x's for every coordinate. Now, remember what I said about those special right triangles, how we were going to use them? Well, here they are. Special right triangles, let's add another note. How about right over here? Yeah, let's do it right here, okay. Remember that we have 2 cases of special right triangles. We have one that looks one short side, one long side, and then we have an isosceles right triangle, where 2 sides are the same length. And the short side, long side triangle, well, that's our 30, 60, 90 triangle. Here's 60, here's 30. And these always have the same ratios of side lengths, where this long side opposite the hypotenuse, that's the same as saying the radical 3. The short side is 1, and the hypotenuse has a value of 2. For our 45, 45 triangle, our same side, same length sides are both radical 2 over 2. And the hypotenuse is 1. All right, I just realized that's pretty small. Here's a little preview, a little close-up of what I just wrote, if you needed a little bit better of a visual. Okay. Now we're going to use those to help us. We can create these triangles. I'm going to use a pencil and then I'm going to erase. We can create right here at our first point, you guessed it, it's written right there, a 30, 60, 90 triangle. How cool. And we can use our cosine to get our x, and we can use our sine to get our y. So our cosine is that adjacent over hypotenuse. So here's the angle we're using. The adjacent side would be this guy right here. And if we look at our reference special right triangle, we know that that is going to be the square root of 3. And then we say over the hypotenuse, and the hypotenuse of our special 30, 60, 90 is 2. So there we go. Our x-coordinate is square root of 3 over 2. Now to get our y-coordinate, we have to do the sine. So the opposite side from this reference angle is our short end. And our short end for our 30, 60, 90 is 1. And we say over the hypotenuse length, and the hypotenuse length is 2. And there we go. That's how we find each and every coordinate. I'll do the next two for this quadrant. Let me erase this in pencil so we can just keep creating these triangles. And if you're wondering about what to write and how to show all of this work, I'm not requiring that you draw all of these special right triangles with me, but I just do expect to see a filled out unit circle on your notes. All right, so this next special right triangle we can see, kind of gave it away already to ourselves, is going to be a 45, 45 right triangle. So we're going to use those properties to help us out. To get our x value, we're going to look at cosine. We're going to look at the adjacent side to this angle, which is this side right here, square root of 2 over 2. All right. We know that's going to be the top of our fraction. We know we're going to have square root 2 over 2 divided by our hypotenuse value, which for this special right triangle is 1. But we know that anything divided by 1 doesn't actually change it, so we're going to leave it as square root of 2 over 2. All right, I'm going to erase that real quick. Now to get the sine value for our y, we do the same thing, but we look at the opposite side. Well, the opposite side is actually the same length on this special triangle. So again, we have square root 2 over 2 divided by 1, our hypotenuse. And we know anything divided by 1 doesn't change it at all. So we have square root 2 over 2 again. All right, one last triangle to draw here. Let's erase these lines. Okay. And again, we kind of already gave it away to ourselves because we already wrote our angles out. We are going to be doing a 30, 60, 90 triangle. So here's our triangle. Here is our reference angle. We're going to take the cosine first to get our x. So we're going to look at the adjacent side to our 60, which is 1 over, and then we're going to have the hypotenuse, which is the square root of 3. Now, if you'll remember, this isn't how it looks on your unit circle because we have to rationalize this denominator. Remember, we can't have radicals in the denominator ever in algebra. So you would rationalize that by multiplying top and bottom by the square root of 3. Oh my goodness, I made a mistake, didn't I? This should not be radical 3. We have to look at the adjacent side 1 and divide by the hypotenuse, not radical 3, but 2. Oh, my goodness, good thing I caught that. So the x value here, your cosine would be 1 over 2. And then to get your y value, your sine, you have to take your reference angle 60 and you have to look at the opposite side. In this case, that would be radical 3. And we put it over the hypotenuse value, which is 2. And there we go. That's how you create all of these coordinates. I'm not going to keep going through on this whole circle and do special right triangles for all of these, but you can see how it's created. And I am not going to even require you to continue to fill out the coordinates for the rest of the circle. We just have to do these 3 because I already gave you that handout in class, and this really isn't new information. I just wanted to show you how we come about those coordinates. Okay. Moving on from our unit circle. We're going to talk about the period of a trigonometric function. Now, remember that the period just means how long it takes for the graph to repeat itself. Okay. So when we're talking about, say, the graph of a sine function, the period of the sine function is really just how long it takes for the sine values to repeat themselves. So if we take a look at our unit circle, we can see that we have sine values for every quadrant until 2 pi, and then they start to repeat themselves, right? We have to go around the whole circle till 2 pi, and then they repeat. Go to 2 pi, then we have the same ones. Go to 2 pi, and then we have the same ones. So we know that the period of a regular sine function is going to be 2 pi because that's how long it takes for your values to come around that circle again. And we're going to demonstrate that graphically too. So I'm going to show you on the calculator what I mean by this. It's really going to help illustrate this. So if we turn on our calculator and we go to y equals, and we type in sine x, I'll clear that out, I'll just type it in with you guys, sine, which is down here. And then we press x, and it's right next to stat, all those variables. And then you close your parentheses. And now go to window, and we're going to do something really neat here. To better illustrate the components of the sine function, we're going to change our window. So for our x-min, we're going to say negative 2 pi, and here's how you can do that. You type in negative 2, and then you can press second, and that little caret button, it's right here below clear. That's where pi is. And then you can make your x maximum values 4 pi. So you're going to press 4, and then second, and that caret button again. And our scale, just to really show what's going on here, we're going to press second and then pi, and we're going to do pi over 2. Because remember, if you look at your unit circle, pi over 2 is where sine crosses 0. or pardon me, sine goes up to 1. That's going to be sine's relative maximum. And then if we go down to our y minimum, we're going to make it -2. Our y max is going to be 2, and we're going to go by 1s for our y's. Now we're going to graph this thing. Let's see what it looks like. All right, so it's showing up. And here's what's really cool about the sine function. As you can see, our x values are those radians, right? We made them radians when we just typed in our window. We did them every pi over 2. And so we can see that every 2 of these is every pi, and every 4 of them is every 2 pi, or every 4 of them is 1 rotation around that circle. So it's pretty cool stuff. If we block it off, let me get my Post-its. If we sort of block it off and just take a look at what's going on for every 2 pi, all right, this is 1, and then if we look at every 4, we can see that this is what sine is doing. And this makes sense because, again, if we look at our unit circle, we know that sine starts at 0, goes up to 1, goes back down to 0, goes to -1, and then goes back up to 0. And by the time it's back to 0, that's when it starts going around the circle again. So that, if you remember, is how those trigonometric functions are graphed. The x values are the radians, and the dependent value, or pardon me, the dependent values are just whatever was in this coordinate, right? Okay. So, using that to kind of visualize here, remember this piece of information from our last video when we had y equals a sine of b x minus c plus d. And we talked about what each of these pieces does, right? Where a, that is your amplitude. Also, your vertical stretch or shrink. And B was called your period, but I don't really want you guys to think of it like that just yet. It does have to do with your horizontal stretch and shrink. But here's the thing, your period value actually comes from this ratio. Your period value actually comes from 2 pi over this absolute value of this b. And here's why. Remember when I showed you on the unit circle that a period is how long it takes for a graph to repeat itself, and it takes sine a whole rotation of the circle to repeat itself. It takes sine a whole 2 pi to repeat itself. So that being said, when we have no b value, or pardon me, we have a b value of 1, so it doesn't really show up, then we have a regular rotation, right? We have a rotation of 2 pi, just like it normally would be. But that's why it makes sense that when b is greater than 1, we would plug that into here and we would get a smaller value. We would get a shrink of our graph. If we made that b smaller than 1, we'd have a decimal. Oh, pardon me, there's 1. If we made that b smaller than 1, we'd have a decimal on the bottom. We'd have a bigger number here for our overall period value, and then that would stretch our graph horizontally. So I'm hoping that that makes a little bit more sense now that we reviewed the unit circle as well as the sine function. Now, there's one last topic I'd like to talk about, so we're moving on. And we're going to talk about properties of the 6 inverse, I'm going to abbreviate, trigonometric functions. Whew, that's a long title. All right. And I want to review one vocab term with you for this, oscillation. Oscillation just means when a graph continually moves up and down. And we saw that trigonometric functions always do this because they're by nature a part of that unit circle, and they just keep going around and around and around that circle. They go up and they go down, and that's just what they do. That's how we graph trig functions. But an important thing to remember is that in order for a function to have an inverse, it needs to be able to pass the horizontal line test. And we know, just by thinking about it, that something that oscillates won't ever pass that HLT, won't ever pass the horizontal line test. But we can do something with our trig functions, and here's what we can do. Draw this graph with me. We're going to draw out our sine function again. We're going to label every -1, every +1. We're going to go by pi over 2 on our x-axis. Again, I'm just counting by halves here. Okay, and if we remember how that sine function behaves, we have a beginning here at 0, 0, and then at pi over 2 it comes all the way up to 1. At regular old pi we have a value of 0 for sine. At 3 pi over 2 we have a value of -1 for sine. At 2 pi we hit 0 again. At 5 over 2 pi we have a 1 again, and then at 3 pi we come back down to 0. Make sure you have arrows at the ends of your graph, always. Okay, so this is our sine graph. Like we talked about, this will never pass the HLT just by looking at it, we know. But what we can do with trig functions is pretty interesting. If we break them up, I'm going to take some Post-its to show you what I mean. If we break them up into sections, so say we broke them up, the sine function, into every pi over 2. Check out what just happened. For this one range of pi, from the range of pi over 2 to 3 over 2 pi, this little section of sine of x, this does pass the HLT. For this section, for this domain restriction from pi over 2 to 3 over 2 pi, we can, in fact, have an inverse. And so that is where inverse functions come from. So write this part down with me. Sine of x is 1 to 1 for the interval, or on the interval, what we just found, pi over 2 to 3 over 2 pi. And these answers can, oh, pardon me, that's supposed to be bracket, okay. If you look, these intervals can also change, right? It could be pi over 2 to 3 2 over pi. It could be 3 over 2 pi to 5 over 2 pi. You have a lot of different options. It's not just one domain restriction. And so we know that it's 1 to 1 for this interval, so that means that for that interval, and all the other ones I just pointed out, arcsine of x, or I should say the whole function, right? Pardon me. Make sure you have your y equals in there. Y equals arcsine, or in inverse notation, sine to the -1 of x, does exist for the domain of -1 to 1, and the range of this interval, pi over 2 to 3 over 2 pi. And remember, that may look a little bit backwards, but it should look backwards because it's the inverse. So what our domain was for the original function, remember, is our range for the inverse. And what our range was for the original is our domain for the inverse. Okay. And these properties are true for all of our trigonometric functions. All of our trigonometric functions, so cosine of x, tangent of x, what else do we have? Cotangent of x, secant of x, cosecant of x. All of those functions do then have inverses if you restrict their domain. So you just have to be careful about where those restrictions are, right? You have to make sure that it will pass the HLT within whatever interval is stated. Okay, that was the last little piece of trig that I needed to show you, so we'll see you in class tomorrow. Thanks for watching.